Hi guys, welcome back to my channel. I'm also Cordil. Today I'm continuing with the loss of weight due to sudden contraction here, and we have already done the loss of weight due to sudden enlargement in our previous video. I recommend you all of you to watch that video and come to this video after that. Okay. So here we're dealing with the minor loss in the pipeline, and these are the sudden contraction, sudden enlargement are called minor head loss. Minor head loss. Also, you can see this is a point loss. Point loss. It occurs at a point, so that's why you can see this is a point loss. And besides it, there is another loss, that is a major head loss, which occurs on the length of the pipeline, which is given by the DeCH2.1 equation, and I have already made the video of DeCH2.1 equation in my YouTube. Okay, that is called a length loss or major loss, but now we are dealing with the minor loss in this case. And here a sudden contraction is occurring, so that's why initially the pipe runs the larger diameter, and the contraction occurs just here, and this is a diameter D1 and this is a diameter D2 here, and the discharge is same because these are connected in the series combination, so that's why you can say the discharge is same in this case. And the loss occurs at a point, this is called a minor loss, and it occurs at the transition point. Okay, so the transition point is just a black dot over here, just a point loss is occurring right here. And how water behaves while traveling to the pipeline, the water initially follows the boundary, but when the transition comes, the water goes like this, and the water goes like this, and it makes a vena contracta where the loss is occurring, which is the main part for it is responsible for the loss of weight due to sudden contraction. Okay, this is a vena contracta, you can see here. This is the vena contracta, smallest depth here, and this section is, you can say this section is 2-2. Okay, I am writing this section 2-2, and after the vena contracta, and there is a cross section where there is a section CC. Okay, looking at this part here, the enlargement is occurring from the vena contracta to this section 2. So that's why you can apply the previously derived concept, that is loss of weight due to sudden enlargement here in the case of loss of weight due to sudden contraction. Okay, so let's write some variable here, that is AC is equal to cross sectional area 8 cc. Okay, cross sectional area 8 cc, and BC is equal to velocity 8 vena contracta, that is cc, right? And A2 cross sectional area 8 to 2, and V2 is obviously the velocity at section 2, right? Okay, so now we have written all the variable right here, and we are going to apply the previously derived formula, which changes from this vena contracta to section 2, and it is responsible. So that's why there is a loss of weight due to sudden contraction can be written from the loss of weight due to sudden enlargement. So that's why we have got a formula of enlargement, that is V1 minus V2 whole square divided by 2z. And let's use this enlargement case here in the contraction. In this contraction, the enlargement is occurring from this vena contracta, which is responsible for this minor loss. The minor loss occurring at this point here. So this vena contracta formation is responsible for the minor loss, for the loss of weight due to sudden contraction. So that's why there is an enlargement from this vena contracta to this section number 2. So that's why I'm going to apply here the concept right by using the formula of enlargement. Yes. And now you can see LC over here, because the contraction is occurring from section this pipe to this pipe. So that's why there is an enlargement case here from BC to B2. So that's why you can do like BC square divided by 2z. And LC is equal to, if you do the common here, B2 common, you will get B2 square divided by 2z. That is going to be BC by B2 minus 1 whole square. Okay. So there is equation number. You can say this is equation number 1. You can say this is equation number 1, and you are going to apply the continuity from this section AC to A2. Okay, AC to A2, I am going to apply the continuity. And the continuity equation is what? You are going to apply the continuity equation, that is ACBC is equal to A2B2. So this is the continuity equation, and you are going to get BC divided by B2 here, that is A2 divided by AC. Let's substitute this BC divided by B2 here. BC divided by B2 here in equation number 1. Substituting this equation number 2 in equation number 1, we are going to get some expression, right? So I'm starting from the top, and I'm getting the expression, that is, LC is equal to B2 square divided by 2z and that is BC by V2, that is A2 divided by AC minus 1 whole square. Okay, and the LC is equal to, that is V2 square divided by 2Z 1 divided by AC divided by A2 minus 1 whole square. And what is this AC divided by A2? Here look at this figure. In this figure here, AC, this is the cross-sectional area of the vena conductor, and this A2 is the cross-sectional area of the pipeline. And you have to say that from fluid mechanics, this is coefficient of contraction. Coefficient of contraction, that is CC is equal to AC divided by A2, which is generally given in the question. So if you have the numerical of this type of sudden contraction and sudden enlargement case in your numerical, and you see the coefficient of contraction here, don't assume by yourself the coefficient of contraction. So that's why let's substitute this CC over here. That is, you are going to get LC is equal to V2 square divided by 2Z 1 by CC minus 1 square. So don't forget this is square. And finally you have got this, this one is K V2 square divided by 2Z. This K is our final expression for the loss of weight due to sudden contraction case in the pipeline. So this is our final expression where you have to remember that this K is 1 by Cc minus 1 whole square. Okay, this K is 1 by Cc minus 1 whole square, and this K is equal to 1 by Cc coefficient of contraction minus 1 whole square. If Cc is not given, then you have to remember that this K is equal to 0.5. Okay, at that moment you have to remember this K is equal to 0.5, and the formula become like Yc is equal to, at that moment Yc is not given. If Cc not given, then what will you say? Then K is replaced by 0.5. Yc is equal to 0.5 V2 square divided by 2Z. Just remember that the section 2 velocity is only taking part in this derivation, so that's why there is no V1 square by 2Z. There must be the velocity at the smaller section of the pipeline, where the velocity is V2 is equal to velocity at contracted pipe, smaller pipe, the velocity at the smaller pipe. This is how you do the derivation, and we have just concluded this derivation because we have already done the derivation of the loss of weight due to sudden enlargement in our previous video, and watch that video first and then come back to this video. And if you have any issue regarding this, if you have any confusion regarding this derivation, you can write in the comment box, and we will do astounding, very important type of numericals from this sudden enlargement contraction case in our later videos. Okay, keep in touch with my video. Thank you so much for watching.